Students, let us start with the next session on motion, session 3, which is on acceleration. I am tutor Vinod Menon from Navayug Study. So in the last two sessions we have seen what is distance, what is displacement. We have seen uniform motion, non-uniform motion. We have looked at velocity and speed and what their differences are. And we have found that displacement and velocity are vector quantities. Next important term that you are going to learn related to motion is acceleration. What is acceleration? It is rate of change of velocity, which means that a body is having a non-uniform motion where the velocity of the body is keeping on changing as the time goes. Let us take an example. You are sitting in a car and the driver starts up the engine and then he presses the accelerator. Why is it called an accelerator? Because that is responsible to make the engine generate more power, through which the car starts accelerating, where its speed was initially 0 km/h, and if you start looking at the speedometer you can start seeing that slowly the velocity is increasing to 10, 20, 30, 40 and so on km/h, which means the car has got a non-uniform motion where its velocity is increasing as the time progresses. And this is a situation where we say there is a change in velocity, and that rate at which that velocity is changing is called acceleration. So, which means if you look at the motion, let me just bring up okay, so if you look at the motion, right, and here u is the initial velocity and v is the final velocity and t is the time taken. The acceleration is the change in velocity divided by time, which basically gives what is the change in velocity per unit time. If it was uniform velocity, then there is no acceleration, and that is uniform motion, right, as we have seen before. So when there is uniform motion, there is no acceleration. So zero acceleration for uniform motion. Okay, fine. Now it's not necessary that always the velocity is increasing. It's possible that the velocity is decreasing. For example, you're sitting in a bus is traveling at a velocity of 80 km/h, and the driver applies the brakes. When the driver applies the brakes, if you're observing the speedometer, you can see that the velocity with which the bus is traveling is reducing from 80 to 70 to 60 to 30 to 20, and sometimes even it comes all the way to 0 and the bus comes to a state of rest. So even that is an acceleration, but it is actually not acceleration. It is called the deceleration or negative acceleration. It's also called the deceleration. Of course, it's very obvious that acceleration is a vector quantity. It's a vector. The reason is because it is rate of change of velocity, and velocity is a vector. If the velocity is a vector, then of course the acceleration has to be a vector. So both velocity and acceleration are vector quantities, where we have to look at the magnitude and also the direction of the term as we discuss it. So when there is acceleration, or when there is deceleration, there is non-uniform motion. The acceleration can be positive where the speed is increasing, or the acceleration can be negative where the velocity is decreasing. So if the velocity is increasing, it's positive acceleration, and if velocity is decreasing, it's negative acceleration, which is also called deceleration or retardation. So these are some other alternative terms which is used for negative acceleration. So now that we have discussed about the basic term acceleration, let us look at what is uniform acceleration. We have seen what is uniform motion. In the case of uniform motion, you are talking about a body which is moving with uniform velocity, which means the amount of displacement in equal intervals of time is going to be the same for uniform motion. But what about uniform acceleration? In the case of uniform acceleration, what you're saying is the rate of change of velocity or velocity change in equal intervals of time is going to be the same. So here you can see, if a body travels in straight line, there's no change in direction, and its velocity increases by equal amounts in equal intervals of time. So of course the important aspect of should be in the same, no change in direction is very important, because it's possible, as we have discussed before, it's possible that the body has uniform speed but doesn't have uniform velocity. Why? Because it's possible it's keeping on changing its direction. We have seen the example where a car was turning on a bend and it had uniform speed but it didn't have uniform velocity because its direction was continuously changing. So when you're talking about change of velocity, it can be change in its magnitude or it can be change in its direction. And when you discuss about circular motion, we will see a scenario of acceleration where the speed is constant but there is still an acceleration. We'll discuss that later. But let's come back to this definition. So here we are saying that a body is moving in a specific direction and its velocity is increasing by equal amounts in equal intervals of time. And if you look at a velocity time graph of a uniformly accelerated body, it's going to look like this. So here you can see the relationship between velocity and time is linear. It's a linear relationship between velocity and time. And you can see that if you take two instances of time, t1 and t2, v1 and v2, the acceleration is v1 minus v2 by t2 minus v2 minus v1 by t2 minus t1. And if I take another interval, probably of the same amount, like t3, and you can see v3 minus v2 by t3 minus t2 will also be the same. So because it is uniformly accelerated motion. An example that you can take for a uniformly accelerated motion is freely falling body. A freely falling body has got a uniform acceleration, and how much is that acceleration? The acceleration for a freely falling body is what is called the acceleration due to gravity. We'll discuss that in gravitation later on. We'll derive the we'll derive the exact equation through which we can compute the acceleration due to gravity. So acceleration due to gravity, and it is usually represented by g. So when a body is freely falling, that means I go up the terrace of the building and I just drop a stone. The only force which is acting on that body, the stone, is a gravitational force, and it will fall down with a uniform acceleration, and that acceleration is going to be acceleration due to gravity, which is called g. And in that situation, the velocity time graph of that body. Of course, initially it starts with 0 and it keeps on increasing, and it will have the highest velocity when it hits the ground. The velocity variation with respect to time will be a straight line graph, which is also called a linear relationship. So I hope this is clear, right? And you've understood the concept of uniform acceleration, right? And we have taken an example of uniform acceleration, which is a freely falling body. Now let us look at what about non-uniform. Non-uniform, it's not non-uniform velocity, it's non-uniform acceleration. I'm sorry, I'll just correct it straight away. Accelerations. Sorry for that. So if you look at non-uniform acceleration, how does it look like? Now you can see here the velocity time graph is no more a straight line, right? So you can see the velocity time graph is like a curve. You can see the curve here, and initially here in this place the velocity is increasing, then it reaches at some point here, then after that it is decreasing, then it is increasing at a far more higher rate than here. You can see that suddenly there's a steep increase in velocity. So across this whole motion of the body, you can see that the velocity variation of the body is not uniform. So which means it's a non-uniformly accelerated. It is non-uniformly accelerated motion, where if you look at the motion, you can see that the rate of change of velocity is not a constant. If it had been a constant, it would have been a straight line like that, but it is not. For example, if you look at a rocket launch, right? In the case of a rocket launch, you can see that the velocity variation is not a constant. Initially there will be certain acceleration, it keeps increasing, the acceleration keeps increasing, right? So there is a variation, and rocket launch is an example where you don't have a uniform acceleration. And since it's not a uniform acceleration, the path, the velocity time graph will not be a straight line, it will be a curve. So this is an example of a body which again depicts a non-uniformly accelerated motion. Okay. So let us just move to the next term, which is average velocity. Now, what is average velocity? If assume that a body is uniformly accelerated, that's a very important point. Now, whatever the average velocity that you're talking about, this equation applies to a uniformly accelerated body. So you cannot use this equation if the body is non-uniformly accelerated. That means the body doesn't have a constant acceleration, right? But let us assume that you have a body and it is uniformly accelerated with certain acceleration. In that case, you can actually find the average velocity by using this equation. Now, what are you doing when you're finding the average velocity, right? So let us look at that. So let me so let us first draw the graph. So if you are having a uniformly accelerated body, the velocity time graph is going to look like this, right? So this is velocity, this is time. Okay, velocity time graph will look like this. Now, so say I am looking at motion between two instances of time. Okay, two instances of time. This is t1 and oh sorry, this is let me draw that line once again. So two instances of time t1 and t2. So velocity here is v1 and velocity here is v2. Now if you want actually to find the effect, ultimately the effect of the whole thing is that the body is going to move, right? Now what, by computing the average velocity, what you're saying is the body moving at a uniform acceleration like this, from with the velocity v1 at t1 and v2 at t2, is equivalent to the body moving at a uniform velocity at a between these two instances at a uniform velocity of v1 plus v2 by 2. So this non-uniform velocity motion is equivalent to a uniform velocity motion with a velocity of v1 plus v2 by 2. That is the meaning of a average velocity. And many cases the average velocity is used for ease of computation, right? And please understand the concept. So by finding the average velocity, we are basically saying that it is equal to a non-uniform velocity motion of v1 to v2 in between these two times. So I can replace that with a uniform velocity motion. So it is equivalent. That is basically what it means. Okay, fine. So that is the average velocity, and average velocity can be found, and this, as I told you, only applies to a uniformly accelerated body. If it is not uniformly accelerated body, you cannot use this equation. Fine. So with this we are coming to an end with the session on acceleration. I hope you have understood what is acceleration. We have looked at how a velocity time graph for a uniformly accelerated motion is. We have found acceleration as a vector quantity. It can have, there could be positive acceleration or negative acceleration, which is also called retardation or deceleration. And we have looked at the velocity time graph of uniformly accelerated body and non-uniformly accelerated body. These are the contact points if you want to get in touch with us, navayuk.study@gmail.com. Please do visit our e-learning site, http://navayukstudy.in/e-learning. Thank you.